Okay, thank you all for coming. My name is Maria Antonia Zahlbruckner. I'm a researcher at the TU Wien in Austria at the Faculty of Civil Engineering within the Department of Integrated Planning and Industrial Building. Today I'm presenting to you the evaluation of our parametric multi-objective optimization and decision support tool for flexible industrial building design. The tool itself was developed and tested within the course of our ongoing research project BIM-Flexi. So some of our nowadays obstacles within industrial building design are the rigid structural building systems that can hardly adjust to dynamic production processes. We have a lack in tools which help with decision making to consider sustainability and flexibility criteria. And applying the state-of-the-art planning method, disciplines plan sequentially instead of working with interaction and feedback loops in early planning phases. So while industrial buildings are the reason for a significant amount of resources, waste and energy, we still work with manual design exploration, which is ineffective and very time-consuming. So with our research project BIM-Flexi, we aim to overcome some of the obstacles with industrial building design and develop an integrated industrial building design process where sustainable and flexible buildings are designed considering dynamic production processes. We developed methods for automation of design tasks to contemplate design desires and automatically calculate production layout scenarios, as well as the load-bearing structures. And to improve the building's outcome with measurable criteria towards more flexibility, the building's life cycle costs, and the environmental performance, evolutionary algorithms for multi-objective optimizations were developed. With BIM-Flexi coming to an end as a research project in August, actually 3 tools were developed. We just tested one within this user study that I'm presenting today. We tested actually the second one, the parametric model for multi-objective optimization and decision support that automatically analyzes the structural design's performance with a parallel assessment of its life cycle costs, its life cycle analysis, its recycling potential, and the flexibility ratings. So for the evaluation of our parametric multi-objective optimization and decision support tool, we compared 2 approaches. For once, the participants of the study tested the POD tool, where they manually generate structural building options by manipulating the variable parameters in the tool and analyze their performances. Therefore, the attendees identified parameters to their needs, listed 3 to 5 variants, and entered the BOT tool. They assessed the outcome and listed the results to further decide on a final variant. Afterwards, they were asked to fill in a questionnaire. The other approach, testing the PMOOD tool, the participants investigated the automatically generated building variants generated by the algorithm and also chose 3 to 5 variants to further discuss and evaluate within their design team. We also asked within this approach to list the parameters of the chosen building variants and to decide on a final variant. Also, after applying this method, the attendees filled in the questionnaire. So this user study was conducted to answer the research question if the satisfaction with process, outcome, collaboration, and with technology is rated higher when employing the PMOOD tool rather than handling the POD tool with manually set parameters. So the structure of the within empirical research conducted experiment included 36 students of the TU Wien. Among the participants, a rough distinction was made between architects and engineers. So 18 groups of 2 were randomly generated and built design teams that all tested both introduced approaches. The participation was not limited by any previous knowledge about optimization or parametric modeling. Therefore, all students had to attend a 2-hour tutorial the day before the user study. On both testing days, the user study and its aim were introduced, as well as both approaches. Furthermore, the design task and the designer's goal were defined. Following that, the 2 approaches were tested with a subsequent questionnaire on a respective tool. To prevent the participants from learning the procedure, the order of conditions was randomized across the design teams. So as the design task, the participants had to design a structural building around an already generated production layout with outer dimensions of 210 and 130 meters. The industrial production building is located in Tyrol, in Austria, and holds sanitation systems with a gross area of roughly 60,000 square meters. So the goal for the attendees was to find their subjectively best solution for the given input, considering the structure's flexibility, its life cycle costs, and the life cycle analysis. So through questionnaires for each approach filled in by every participant, we were able to gather quantitative as well as qualitative data. For quantitative results, the users' satisfaction on people-process level and their satisfaction with technology were investigated. 3 subcategories were requested in detail regarding the satisfaction on people-process level, their satisfaction with process, outcome, and collaboration. Other questions based on the technology acceptance model evaluated the tool's ease of use, its usefulness, and its visualization. So for the quantitative evaluation of the questionnaires, the response options were rated from 1 to 5, implying strongly disagree with 1 and to strongly agree with 5. And the results are here presented by field in order to interpret the results to the different goals and perspective of the 2 main disciplines, which were architects and engineers. Regarding the technology acceptance model, the engineers ranked the POD tool higher than architects in every subcategory. Visualization is rated highest by both disciplines amongst the subcategories of ease of use, visualization, and usefulness. Engineers rated it with 4.59, while architects stated their satisfaction with 4.19. Regarding the satisfaction on people-process level, the subcategories collaboration and outcome are ranked higher by the architects than by the engineers. The attendee satisfaction with the process was higher rated by the engineers. The questionnaire resulted in 4.15. For them, the architects rated their satisfaction slightly lower with 3.97. The same categories concerning technology and work satisfaction were evaluated to investigate the automatic approach. So for this approach, the results suggest that the participating engineers were more satisfied with the usefulness and the visualization regarding the technology acceptance model. For the subcategory ease of use, the architects rated their satisfaction with 4.09, while the engineers were slightly less satisfied, resulting in a rating of 3.85. On people-process level, architects rated the lowest ranking within their process satisfaction with an average of 3.62. Engineers were least satisfied with the outcome, ranking on average 3.92. The attending engineers ranked their satisfaction with collaboration and process higher than the attending architects. So the comparison of the POD and the PMOD tool, evaluating the service across all disciplines, shows that the overall satisfaction is higher with the manual tool, so with the POD approach. For both main categories, satisfaction with technology and on people-process level, every subcategory was ranked higher for the manual tool approach. Regarding the assessment of work satisfaction, the evaluation reveals that process satisfaction is perceived as the category with the lowest performance for both approaches. So for the POD, it says 4.03, and the PMOD 3.81. The questionnaires also revealed the highest difference in performance amongst the 2 approaches in the subcategory satisfaction with outcome by the difference of 0.35. Results for the technology acceptance model show the subcategory of visualization performed highest in both approaches, for the POD with 4.33 and the PMOD with 4.28. So while the automatic approach is rated on average with 4.09, the manual approach has an average rating of 4.29. Also, 3 open feedback questions were asked at the end of each questionnaire and represent the tool's qualitative assessment. Suggestions for improvements on the satisfaction with process, with the handling, the visualization, and how to make collaboration more effective and interdisciplinary decisions more accessible were requested. So participants stated storing variance while manually setting parameters to investigate another option as a possible improvement. Concerning the manual approach POD, replying to the specific survey for the automatic approach PMOD, a more refined user interface with detailed description of the MO output was suggested. Many participants also asked for the prospect of a more specific visualization of the variance material. While the tool assigns for now indices for each material, the users would understand names or colors within the output as a better guidance. And 1/3 of the participants also argued the missing transparency of the output's calculations concerning the life cycle costs, the CO2 output, and the flexibility rating within both approaches. So the overall qualitative assessment suggests a higher preference of applying the POD tool rather than the PMOD tool. While the subcategory of collaboration within the assessment of satisfaction on people-process level performed highest within both approaches, The subcategories regarding the satisfaction with process and outcome were rated lowest. Regarding the technology acceptance model, ease of use was the category where the most improvements were seen. Differing amongst the disciplines, engineers were more satisfied with the technology regarding usefulness and visualization, while architects stated the ease of use higher than other subcategories looking at the technology acceptance model. Qualitatively assessed, questions indicate the tool as a great assistance in early planning phases, where several different disciplines can work simultaneously. Despite the overall better performance of the POD tool and the restricting condition of the limited exploring design space, the PMOOD tool ratings are in 5 out of 6 requested categories on average stated higher than 4, with the highest possible rating of 5. Therefore, the higher ratings indicate that the tool helps in early planning phases, designing more flexible, economically and ecologically sustainable structures designed for an industrial building's life cycle. The next steps within our research project are, for once, the meanwhile conducted testing of our coupling the PMOOD tool with another tool that was developed within our research project, the multi-user VR. And furthermore, the simplification of the user interface as well as the overall handling of the tool. And one part that is constantly under development is to minimize our calculation time. Thank you very much for your attention.
Thank you.